Welcome to the lesson on circular motion. In this lesson, we're going to discuss the mechanics of objects that travel in circular paths. And a little later on, we'll also discuss how to convert from linear to angular quantities in case we see that pop up, and it does come up once in a while. This diagram shows an object traveling in a circular path. We can consider this to be the top view of an object traveling in a circle. And we're going to say that our object here is traveling at constant velocity v. One thing to note here is that at any given moment during the rotation around in the circular path, that the velocity is tangent to the circular path. And so each of these arrows being labeled represent the tangential velocity of the object traveling in the circular path, and that velocity remains constant. Well, yet this object is accelerating, and we call that acceleration centripetal acceleration with the label A subscript C. Now, why is that? The reason that it's accelerating is because though the magnitude of its velocity is not changing, the direction of the velocity is constantly changing at any given moment. So that acceleration, we give a special term. That acceleration is called centripetal acceleration. Centripetal acceleration is given by the equation v squared over r. We're not going to take the time in this lesson to derive where that comes from. Your textbook does do a nice job showing that derivation, so if you're interested, I would encourage you to look it up. So that's how you calculate its magnitude of the acceleration. Its direction is that it is always pointed towards the center of the circular path. Newton's second law would dictate, and if you may remember from our study on Newton's laws, that if an object is accelerating, there must be a force that's proportional to that acceleration causing the acceleration. So indeed, we have a force proportional to that centripetal acceleration, and we of course call that centripetal force, F subscript C. Derived from F net equals ma, the net force acting on the object, we would then of course ask ourselves, is this object accelerating? In these types of problems, though the object may be moving at constant velocity, sometimes it's also not. We'll get to that later. The reason we say yes, it is accelerating is because it's traveling in a circular path. So we put our subscript C on the A, and so the net force is caused by whatever's causing the centripetal force, which is MAC. And substituting the equation for AC, we get this centripetal force equation, mv squared over r. Centripetal force is difficult at first for many students because it feels very mysterious to them. For example, if you're in a car and you're going around a corner in a turn, you do not feel pulled towards the center of that circular path. You feel your body lean outside, away from the center of the circle. So because you don't feel pulled towards the center, students often have trouble identifying with what centripetal force is and that how to calculate it, and that it feels very mysterious to them. Because your personal life experience is not that you're pulled towards the center, but that your body leans, in fact, almost feels pushed towards the outside. A point of clarification on this is that it is not a force that is causing your body to lean towards the outside of the circular path. It's rather your body's inertia, your body's tendency to resist changes to its state of motion that causes your body to lean towards the outside of the circular path. Your body wants to stay straight, but the car or object that you're attached to in the meantime is turning towards the inside of the circular path, making your body feel like it's pushed to the outside. Please remember that inertia is not a force. So the reason you lean towards the outside is because your body's tendency to want to stay straight while the object that you're attached to turns in the other direction. All right, we're going to move on here to one very, very important point, and that is that centripetal force is always caused by some other force or interaction, summation of forces. Forces that can cause centripetal force include friction, specifically static friction, tension in strings or ropes or cables. Gravity can cause centripetal force, and we have a nice tie-in later in our unit with that, where universal law of gravitation is applied in a centripetal force context. And normal force, if the object is resting on a curved surface that goes over the top of that surface or towards the bottom of that surface. With all summations, just like we did in our previous unit, we would start out by saying sigma f equals ma. Is our object accelerating? The answer is yes, because the object is traveling in a circular path. Some examples of summations you may see, for example, we never write FC equals MAC, substituting that in for sigma F, because the centripetal force is always caused by some other force. Instead, we would see things like static friction causing the mass to centripetally accelerate, or tension causing the mass to centripetally accelerate if it was being whirled in a horizontal circle. What if it was being whirled in a vertical circle? Well, at the bottom, you can imagine the tension in the string is up and the weight is down. So the summation would end up being T minus mg equals MAC. Now, an important point here, this is for an object being swung in a vertical circle attached to a rope or a string. An important point here when you summate, when considering problems involving centripetal force, is that the center, remember that we would always say that the direction of motion or intended motion is always positive. Well, in centripetal force summations, the intended direction is towards the center of the circular path. So positive in centripetal force summations, positive is always deemed to be towards the center of the circular path. That's why in this summation that we just wrote, T is positive towards the center, mg is down when the object is at the bottom half of the swing there in a vertical circle. If it was at the top of the swing, both the tension and the weight are pointed towards the center of the circular path, so our summation would be T plus mg equals MAC. Okay, and that's when the object is in the top of the circular path when it's being whirled. If you have any questions on this, ask in class tomorrow, and we'll have much, much more practice with Newton's second law summations involving objects traveling in circular paths, therefore having centripetal force. Okay, we're going to wrap up this discussion by talking about converting from linear to angular conversions. We're first going to talk about that and then talk about centripetal acceleration and alternate equation for that. And you can see what's set up here is that what you do is you take your linear quantity, which is always equal to the radius of the circular path times the angular quantity. So let's start out with distance. The symbol for distance for us is x, and we of course measure that in meters. Well, that equals the radius times angular displacement, which would be what symbol? You may recognize this from your math class. Angular displacement is theta. And we would give that in radians. Angular displacement is in radians. So if you want your linear quantity, if you want your displacement in linear form, you take the radius times the angular displacement, and that would give you your linear displacement. What about linear velocity? Well, the units of linear velocity is meters per second. How would we calculate it? R times angular velocity. The symbol for angular velocity is the lowercase Greek letter omega, which is basically a curvy W. Our units of angular displacement, angular velocity would be radians per second, similar to meters per second. What's next? Acceleration. Linear acceleration in meters per second squared would be our radius of our circular path times our angular acceleration, and the symbol for that is a lowercase Greek letter alpha, which kind of looks like the fish symbol. And this, of course, would be radians per second squared. So that's how you convert back and forth between linear and angular quantities. Now, sometimes if in a problem, if we're given the angular velocity, we could quickly and efficiently calculate the centripetal acceleration given the angular velocity by the following derivation. If we start out with AC, the definition being v squared over r, and we sub in for v the angular conversion to that, which I'll underline here in blue, which is, of course, r omega. So in place of v, we substitute r omega. We then square it and place it over r. R omega squared would be r squared omega squared. And of course, what happens is that the r cancels out one of the squares, and we end up with r omega squared as another way to calculate centripetal acceleration. The usefulness of this, and I would encourage you to add this to your reference table, the usefulness of this is that if you're given the angular velocity, you don't have to convert to the v. You can just directly substitute in and go r omega squared equals your centripetal acceleration. Okay, much more on circular motion problems as we begin work in the problem set coming up. And if you have any questions, make sure you ask in class.